So this lecture we're going to talk about integrators. Integrators are basically a mathematical function. What we're doing is we're just adding up. We're keeping track of something and adding it and adding it and adding it to find the total sum. So a couple of examples here. A couple of examples here will be energy consumption. So if you think about the electricity coming into your house, there's a meter out there that measures the current. Remember that power is voltage times current, and energy then is power times time. So when we buy our electricity, or we pay for our electricity, we pay per kilowatt hour. So that is watts times time. Watts times hours, or kilowatt hours. Another example would be, say, the amount of material being transferred across a conveyor. So we could look at the total amount of material, how many tons of material has been hauled. So we can calculate the flow rate. So if we know it's doing 1 ton per hour and it's been moving for an hour, then it moved 1 ton. So that is how we can determine the amount of material. Now if we do that for 24 hours, right, 1 ton per hour for 24 hours, we add that up, 1 ton every hour. After 24 hours, we've added all the way up to 24. So a large majority of the integrators are integrating versus time. It doesn't have to be versus time, but that is one of probably the most common use of an integrator, where we're integrating versus time. So what does that mean exactly? So if we have a value that is moving, such as shown in here, so we have this waveform that is moving as time moves, then what we want to do is we want to add those up. And so to do that, we basically need to calculate the area. So when we calculate the area, we could use a trapezoid. So if you look at, say, this example right here, where we have this line going from here to here, so, we have a line from here to here, and if we map out this like box here, this is almost a trapezoid. So this area here is basically a trapezoid. So the area of the trapezoid, is given as the distance in the horizontal direction, which if this is time, the horizontal direction is time. So we have this point, which we call T2, minus this point we call T1. So the area of the trapezoid is 1/2 the base times the first height 1, plus the second height 2. And the base is the time, T2 minus T1 is our base. So that gives us the horizontal piece, and then we have to do the height. So if this is power, if we're trying to measure electricity and we're measuring power, then we pick this point, which we'll call P1, and this point, which we call P2. So those are our two heights. So we would have 1/2 times the base, which is this time step here. We could use a timer for that, so it would be the preset of our timer if we were using a timer inside of our ladder logic. So it'd be 1/2 times the preset times the first power plus the second power. All right, and that would give us how much energy was being used within this one trapezoid. Okay, so that's the area being used within this one trapezoid. However, we need to add that up, right? So we're going to add this up over time. So as time goes and goes and goes, we're going to be adding these all up. So we need to add this one and add this one to this and add it and add it and add it and add it. That is what we call integration. So the way that we do that is we calculate the area. Now the area for one of these, the area for one trapezoid, okay, so the area for one trapezoid, my units is power times time. So the area for that would be the energy, right? We already said that energy is equal to the power times the time. And so we need to calculate that energy, which is this trapezoid. Okay, so this trapezoid here, we have our time. Okay, so we have the power 2 plus the power 1. Those are our two heights of the trapezoid times the distance in time. And if we use a preset timer, it would be like our timer 1 dot preset, divide that by 2. All right, and this would be the energy for one of these trapezoids. So this is the energy for one trapezoid. And then what we have to do is we have to add that over time. So we take energy, I'm going to spell it out here. We're going to take energy is equal to the energy plus the next rectangle here, or the next trapezoid here. So the next trapezoid is going to be P2 plus P1, that's a P there, times our preset value divided by 2. So if we're always using the same time, the base is going to be the same. Now this one here that's multiple colors, the base isn't actually the same as the other ones, but these ones here, these are the exact same time. And so we're going to take this one and we're going to add it with this one, and we're going to add it to this one, and we're going to add it to this one. So when we do that, okay, our P2 is going to be changing. So we'll notice here, for each one of these, keep leaving it on fill here. So at this point here, let's say for this trapezoid right here, this oops, I got two of them in there. Okay, for this trapezoid here. So for this trapezoid here, this is P2 and this point is P1. However, when we do the next one coming up here, P2 moves. This becomes power 2. And what was power 2 becomes power 1. Alright, and so what we can do is we can simply shift power 2. Okay, so power 1 is equal to power 2. And then power 2, I keep putting an R there. Power 2 is equal to the voltage times the current at the next time. So when the timer goes off, we can calculate power 2. Every time the timer goes off, we can calculate power 2, which is the voltage times the current. But before we do that, before we calculate P2, we're going to capture P2 and shove it into P1, because every time we shift to one of these new trapezoids, our P1 was the old P2, and so we have to shift that. Okay, and so what we're doing is we're shifting here, and we're keeping track as we go along, and we're going to fill up every single one of these trapezoids. So we're just going to fill up every one of the trapezoids, but then we're going to add those. We're adding the previous value to the current value plus the new area, the new trapezoid. And that is integration. Adding, and we're adding it to itself here. Okay? And that is this piece that we call integration. And we use that every single day, right? The electric company is always keeping track of how much power you're using. And so at the end of the month, they send you a bill for kilowatts times time. So if it's been 30 days, right? So how many kilowatts did you use over 30 days? That's the amount of energy that you have used, and that's what they bill you for, is your amount of energy use. Alright, so what we're going to basically do here, these next few slides just try to walk you through calculating the area of a simple trapezoid. But what we're going to do is we are going to, in our next lab, our integrator lab, we're going to kind of pretend we're the electric company, and we have to add up how much energy is being used. So to do that, we just want to review some standard electrical properties. So we have Ohm's law, which is the voltage times the current. The voltage is equal to the current times the resistance. That's Ohm's law. There's also the current divider rule, which might come in useful when you're trying to calculate currents in two parallel branches. Okay. The wire resistance formula, if you remember this from DC circuits, the wire, the amount of resistance in a wire is equal to rho, which is the density, times the length of the wire divided by the area of the wire. Now remember, that's the cross-sectional area, so if it's a round wire, we can look that up using the American wire gauge. We can look up the wire. Power is voltage times current, and then as we already stated, energy is the power times time. So, how do we measure this? Now we're going to have a big power resistor. It's actually only 5 ohms, but it can handle 225 watts, which means we're gonna be shoving up to 5 amperes of current into this resistor. The problem with that, though, is our current meter is going to be one of those converters that we used in the load cell lab, and we can measure current with that current meter. But if we're trying to measure current, we got to be careful, because it can only measure a very small amount of current. It certainly can't handle 5 milliamperes running through it. So what we need to do is we need to build a shunt. Okay, a shunt is a very special conductor that we know the resistance of very, very closely. So we're going to build a shunt so that we can measure the current. We're going to then measure that current, use a converter to convert it into a 4 to 20 milliamp analog signal, and send that into our PLC. Alright, so we're going to have to build ladder logic then that is going to integrate, and it's going to take the voltage times the current to determine the power, and then it's going to integrate the power. Every time the timer goes off, it's going to add the previous amount of energy to the new amount of energy. So I'm just giving you some instructions for the PLC you need to review here. We have RTO, which is a memory timer. Okay, so remember RTO is your retentive. The R is for retentive. That's your retentive timer on. We can just have an ordinary timer on. We're definitely going to be needing to use some compute statements. We can use a move block if needed. We can use an equal block if needed, a multiply block. So you want to review these blocks because we'll probably be needing them in our upcoming lab. Alright, so we need to measure electrical signals. To calculate power, we need to be able to measure current and voltage. Alright. Additionally we're going to use the FactoryTalk software to build an HMI interface to record and plot our power and to display our voltage, our current, our power, and our total energy use. Okay. Alright, so to build the shunt, okay, we have to calculate the circular mills. We have to know the circular mills, which is based on our wire gauge. And we're going to use a length of wire to build the shunt. Now the shunt, again, the shunt is a conductor. It's actually a conductor but we need to know the exact resistance of this conductor. Alright, and the purpose of the shunt is because ammeters, you might have an electric motor that might be running 1,000 amps through it. And the problem is that there's no ammeter that was ever been built that can measure 1,000 amperes. Okay, so you might have this electric motor that's got 1,000 amperes running through it, and you want to measure that current so you know exactly what that current is, but you can't run that through a shunt. So the idea is, or you can't run that through the ammeter. So the idea is we're going to bypass about 99% of the current past the ammeter through the shunt. Alright, so we have to know very accurately what the resistance is in the shunt. We're going to place that in parallel with our ammeter, and then we can, if it's in parallel, we know that it's going to have the same voltage across it as the voltage across our ammeter. And so we can then, using Ohm's law, we can calculate the total current, the total voltage. If we know the resistance and we know the current, we're going to measure the current with an ammeter through the one resistor, and then we'll have the voltage, and we can calculate the current through the shunt. And so the total current is going to be the current through the shunt plus the current going through the ammeter, because the ammeter is going to be in parallel with the shunt. So remember, this is effectively Kirchhoff's current law right here. Alright, so we could either use current divider rule, or we could just use Ohm's law, because remember that the current divider rule is just the application of Ohm's law first to the total effective resistance, and then for a single resistor. So current divider rule is basically just using Ohm's law twice. So it's combining Ohm's law once using total current, total resistance to find the effective voltage, and then using that voltage with the resistance to determine the current through that one resistor. Okay, so current divider rule, and it's given there in the slides, but it's effectively just Ohm's law applied twice. Alright, so here is how we use the shunt. So you see the drawing here, I have a very large power source. So I have this very large power source with a lot of current flowing through it. And so what I need to do is I want to measure the current, but there's so much current flowing that it all can't flow through the ammeter. The ammeter just can't handle that much current. It's going to fry the ammeter or at minimum blow a fuse. And so what we can do there is we can use the shunt so that the majority of the current, is going to go through the shunt, and just a tiny bit of the current is going to go through the ammeter. Okay, and so if we know the resistance of the shunt and we know the resistance of the ammeter, then we can calculate how much current is flowing total through the shunt plus through the ammeter. Alright, and we know if you look at your documentation on your ammeter, it's going to tell you what the resistance of that is. Alright, so it'll give you that. You just have to report that. Or you have to, read the documentation and then you can see that. Alright, so our ammeter then is actually going to be one of those IAMA converters that we use for the load cell. So that converter has an option to read between 0 to 1 milliamp. Alright, so what we're going to do is we're going to build a shunt, which is just a conductor that we know the resistance of. And we're going to wire that in parallel. Alright, so this here is actually a parallel connection. The shunt over here, the shunt is in parallel with our ammeter. Okay, so you see here's the shunt, here's the ammeter. These two are in parallel. Okay, so the shunt is in parallel with that, and we know the resistance in the ammeter. The ammeter is actually going to be reading the current, and so therefore we'll know exactly how much current total is flowing through the load resistor up here. So this is our big load resistor, and we're going to heat this thing up. So you want to be careful in the classroom. If you touch this resistor after you've been putting 3 or 4 amps through it for a while, it's going to get hot and you might burn yourself. So don't leave it at 3 to 4 amps for a long time. Turn your current knob down and restrict the current while you're working and stuff, and you can adjust it periodically when we're trying to mimic power being used in a house or something, turning something on and then turning it back off. Alright, so we're going to use one of these converters as a current meter. We're going to use the other converter as the voltage meter. So this converter number 1 here, is going to be measuring the voltage. Now we're going to use the voltage setting between 0 to 50 volts. Alright. The power supply actually won't give us that much. Okay, the power supply can give us about 30 to 32 volts, but with a 5 ohm power resistor, which is this big resistor here, it's going to, if we had 25 volts through a 5 ohm resistor, that would be 5 amperes. And what you're going to find out when you actually start doing this with a power supply is the power supply can't supply 5 amperes, so it's going to go into constant current mode, and we can get about 2.5 to 3 amperes out of this power supply. Alright, so in reality, the maximum current that we're going to get is maybe about 3 amps. But we're going to plan on a maximum of 25 volts across the 5 ohm resistor. So notice when you make these connections, the voltmeter is connected to the 2 sides of the big power resistor, not to the shunt. So here's the shunt. So remember, the current is flowing through. I'm not showing the current meter at the moment, but 99% of the current is going to flow through the shunt, and a little bit will flow through that ammeter, just a tiny bit of it. But then all of that current's going to come back together and go through our 5 ohm load resistor. Alright, so but we're going to use the converters. The converters are going to convert the 1 milliamp signal into a 4 to 20 milliamp signal to feed the PLC, and the other converter is going to feed a voltage that can range, at least theoretically, between 0 to 50 volts into our PLC. And what we're going to do, again, is we are going to simply add up. We're going to add up the area under the curve here. So we're going to calculate the area of each one of these little trapezoids and add those up and add those up until we have the total energy being used, which is effectively what the electric company does, so that they can bill us on how much energy that they've used.